The properties of the elements are determined to a degree by the effective nuclear charge that the electrons experience. So we use Z to represent nuclear charge. Z subscript EFF is going to be our effective nuclear charge. So the effective nuclear charge is what the electron feels, accounting for all the electron shielding of the other electrons in the atom. So the effective nuclear charge is going to be less than the actual nuclear charge. The difference between the two we call the screening constant, or shielding constant. So for valence electrons, the screening constant, this is going to be close to the number of core electrons. Core electrons are pretty effective at screening the nucleus from the valence electrons. The other electrons in the valence shell, this will have a negligible impact on the screening constant of the other valence electrons. So the higher the effective nuclear charge is, the more strongly an electron is held. And the way that we describe our energy for this, the energy of an electron that is completely separate from an atom is zero. So as it is held by an electron, it ends up with a negative energy, a low energy. So the lower the energy, the stronger it is held by the atom. If we have a smaller nuclear charge, that means the electron is held more weakly and it has higher energy. It's getting closer to being able to escape. So our effective nuclear charge varies on what orbitals we're looking at, because the orbitals have various shapes to them, some of them allowing them to penetrate rather deeply close to the nucleus. So for level 2, the two types of orbitals are double-lobed orbitals. So we have a 2s and 2p. 2s is spherical. Its double lobe comes as an inner layer, like an onion layer, as an inner layer to the orbital. Whereas for 2p, it has two lobes outside, very obvious. So neither of those external dumbbell-shaped lobes has an internal layer. So the 2s orbital having an inner lobe, that inner lobe experiences the nucleus better. So the 2s experiences a greater effective nuclear charge and is more stable or lower energy than 2p orbitals. That's why the 2s orbitals get filled first before the 2p orbitals. And this is how we end up with the ordering on any particular principal energy level, that the S is lower energy than the P, which is lower energy than the D, which is lower energy than the F. So as we go across a row, a period, from left to right on the periodic table, we're adding in protons to the nucleus and electrons to the valence shell. But we're increasing the nuclear charge by adding protons to the nucleus, but we're not increasing the number of core electrons. So the shielding constant is not increasing as we're increasing the nuclear charge. So the effective nuclear charge is increasing. So all the valence electrons are experiencing a larger effective nuclear charge. So this draws them closer toward the nucleus, toward a lower energy, and they're being held more strongly by the atom. So the atom ends up becoming smaller in diameter as you go from left to right across a row in the periodic table. We have different ways of measuring atomic radius, but if we take one way, such as the van der Waals radius, non-bonding radius measured during collision. This is the radius we tend to use for space-filling models of atoms. The bonding atomic radius is estimated from the distance between the nuclei in bonds in molecules. So in general, our bonding atomic radius is going to be smaller than the non-bonding atomic radius of individual atoms. When atoms bond, they end up sharing electrons, so the electron orbitals are overlapping. The electron clouds are interpenetrating each other. So the trends on atomic radius, the biggest obvious trend is that as we go down a group, any group, we are going to increase the radius of the atom because we are adding on additional electron shells. As we go from left to right across a period, we are going to be decreasing the atomic radius. So the area with the largest atomic radius is going to be the lower left part of the periodic table, and the area with the smallest atomic radius is going to be the upper right of the periodic table. The size of the atom shrinks so much as you go from left to right across the periodic table that all of our alkali metals are going to be larger than any of the halogens, regardless of what periods we're comparing. So inside a solid, we can measure atomic radius using scattering of X-rays. As we shoot X-rays into a crystalline substance, they will scatter off the atomic nuclei. And if it's a crystalline substance, it'll create patterns in the scatter that will allow us to interpolate the actual positions of the nuclei in the substance. So this is a representation of our atomic radii. And we have a couple ways that we measure these. Let's see if I have another one here. Yes, I do. So the numbers do change a little bit. If we look at iodine, it's 0.133 nanometers. And over here is also 0.133 nanometers. Here we have lithium of 0.123 nanometers. Down here we have lithium of 0.152 nanometers. So they do change a little bit. Sometimes it's by different methods, sometimes by averaging different data over periods of time. But we see our lithium here is 0.152 nanometers compared to iodine 0.133. So lithium, even though it's the smallest of the alkali metals, is still larger than our largest of our halogens over here. So we see that cesium is going to be our largest element here. We get smaller as you go up in a group, and we get smaller as you go right in the group. We have no simple way of comparing the size directly if we're not going either up, down, or left, right. If we're going at an angle from left to upper left to lower right, there's no simple way of predicting the radius. The radius will change when we ionize a molecule. And if we add electrons to an atom, the effective nuclear charge for the new electrons is smaller, and we're going to end up with a larger ionic radius. So negative anions are going to be larger than the neutral atom they were created from. But if we remove electrons, the remaining valence electrons have a higher share of the effective nuclear charge. They get pulled in closer and are held more strongly, and we end up with a smaller ion, smaller cation compared to the neutral atom. So for nitrogen, we see that the neutral atom is 70 picometers. The negative 3 anion is 146 picometers. The plus 3 cation is 16 picometers, and the plus 5 cation is 13 picometers. So we get larger as we go negative, and we get smaller as we go positive. If we look at an isoelectronic series, that's a group of ions that have the same number of electrons. As we go negative toward the negative charges, we're going to have a lower nuclear charge. That means each of the electrons here are going to be experiencing a smaller effective nuclear charge. They're not held as strongly, so the ion becomes big. As we go toward the positive numbers, positive charges, now we're going to have a higher nuclear charge. Each valence electron is going to be experiencing a higher effective nuclear charge. They're going to be drawn in closer toward the nucleus, and we'll end up with a smaller diameter cation.